like to very, very quickly go through the astronomical heritage of Hindus. Very ancient knowledge is encoded the metaphor of stories. So if you go to very ancient works and look for mathematical astronomy, you're not going to find it. You're going to find stories. And the uncoding of the stories is what contains information. You learn from that. Later periods saw mathematical treatment of astronomy. This is a Siddhantic period. And we'll talk about that just a little bit. So we know that there are star trails. If you look at the northern hemisphere, look to the north skies, you have Dhruva over here. If you keep a camera open in the evening, you'll soon get these star trails that you see over here. And the earliest astronomy is encoded as stories in Vedic literature. We have a story that the Saptarishis encircle Dhruva. Everybody knows the story, right? We are told that Saptarishis go around Dhruva, and that really recounts this knowledge of this information. So the early Indians in the Rig Vedic period already had knowledge of the rotation of the earth of this nature. Early Indians also had a clear idea of the equinox and solstice. In your house, if you have an east-facing window, you look at where the extremal rays of the sun come at 8 o'clock in the morning and make a chalk mark over there, wherever the extremal ray is. Every week, 1 week later at 8 o'clock, make a mark again. Next week, 8 o'clock, make a mark again. Pretty soon you'll find that the sun's extremal rays go from north all the way to the south for 6 months. Then the ray retraces back and goes back to the north for 6 months. So using no more technology than a 6-year-old child with a chalk mark, you can trace out over a period of a year what is the extremal solstice point in the north and the south. You could figure out both of these things. You could also figure out the duration of the solar year. Knowing how much time it takes from here to here, could figure out what is the solar year. You could figure out the equinox position. You could figure out the solstice positions. So our Indians were very, very conversant with these things. Uttarayana, Dakshinayana is mentioned even in the Puranas. They could figure out the length of the solar year. They could figure out that we need to add an Adhikamasa in Rigvedic times itself, that to synchronize between the lunar calendar and the solar calendar, they knew we needed to add a Adhikamasa right in the Rigvedic period. So very, very ancient logic we're talking about. We need to talk about precision, because precision is a critically important phenomenon for us to understand. The Earth, in addition to rotating about its axis and pointing the northern hemisphere to Polaris, it is also tracing a slow path in the sky. What is tracing? The axis of rotation, where it is pointing to. Now we're pointing to Dhruva. Where it is pointing to traces a slow path that takes 26,000 years to complete. And that is the precession cycle. Because of the precession cycle, where we are pointing changes. Today we are pointing at Polaris, but when Yajnavalkya wrote Shatapatha Brahmana, we're pointing at Thuban. Thuban was a pole star. There was a period of time when Abhijit was a pole star, Brahma Rishi, and that is Vega. So precision does this to us. Vrittagarga had already estimated the precision rate at 36,000 years. Vrittagarga, approximately 500 BCE or earlier, he had already estimated this at that time. Bhaskara II, who lived in the 10th century, 11th century, he had estimated this to 25,461 years. Amazing prowess by ancient Indians to have done something like this. So the Indian astronomical model was one of nakshatras and Rashi. I've talked about this in earlier talks too, so I'm not going to spend too much time on this. Bottom line, it was a division of the sky in 13 1/3 degree segments, 27 of them. They also divided the sky in 30 degree segments, the 12 Rashis. And they also had a concept of month. If the full moon appeared over the Chitra nakshatra, that month was referred to as a Chaitra Masa. So Indians in some parts of the country use a full moon as a marker. In some other parts of the country, they use a new moon as a marker. So Amanta month or the Purniya Mantha month. In different calendar systems, you have these things. So they had a concept of nakshatra of the day. They had a concept of a month, lunar month. They had a concept of a solar year. And they were able to now use that knowledge to evolve enormous mathematics to do yugas and other such things. We will see that very, very presently. So here is a listing of the nakshatras in two of our ancient books, the Vedanga Jyotisha, Surya Siddhanta, and the principal star, which is aligned with these things. So this mapping came about when the British came to India, and they asked the Pandits, what is that nakshatra? They'd say what the nakshatra is, and the Pandits and the British should map it to their Western systems. That's why today we have a mapping of this nature. If you're wondering how old is the nakshatra model, well, at least as old as Atharva Veda. Atharva Veda in this particular reference, if you use a Griffith translation, you see I've highlighted some names here. It's talking all over the place over different nakshatra names over here. So at least as old as Atharva Veda, we know that the nakshatra model is that ancient. Ancient Indians also noted something called the synodic and the sidereal months. So from new moon to new moon, it takes 29.5 days, and that's referred to as a synodic month. However, if you go from the nakshatra, if you start at Chitra nakshatra and you want to see how long it takes to come back to that nakshatra, that takes 27.3 days. So there's a difference. There's a difference between these two, full moon to full moon or from backdrop of the skies. Indians knew about these things and they wanted to reconcile between these two cycles in the observed solar year. That gave rise to several insights, the Adhika Masa, the different yugas, the great cycles. We had the 5-year cycle, we had the 19-year cycle, the Samvatsara cycle, 60-year cycle of Jupiter and Saturn, all the way to the Chaturyuga cycles. All of these were outcomes of intellectual expression, trying to make sense of the movement of the heavenly bodies and those kinds of things. So Indians used their brains to try and understand this phenomenon, make sense out of this. That's what gave rise to all of these things. So today we know that we mark the passage of time using the Panchanga. Panchanga is a multi-dimensional measurement. Typically we use a Muhurta, which is a 1/30th of a day or a 48-minute interval, in which you make reference to nakshatra, tithi, vara, yoga, and karana. So these are the 5-dimensional measurements of time which Indians use traditionally, and even today traditional Indians make use of this kind of a measurement of time. I'm not sure you can see this from back there, but I thought I'll very, very quickly give you a brief background on Indian astronomy. When ancient Indians saw the sky, what did they see? So this is today's night sky in New Delhi. So this is the horizon, and this is the west direction, north and east, and this is Polaris. This circle is a precession circle that I talked to you about, and here is Abhijit. And whenever Indians talked about nakshatra for the day, it was always in relation to when the moon appears over the eastern horizon, what nakshatra is it in, what section of the sky is it in. So today, when the moon appears in the eastern horizon, I'm not sure of the time, I can't even read it here, I'm not going to make a guess. But when it appears on the eastern horizon, it appears to be in the Rohini nakshatra. This is Rohini nakshatra. So today's nakshatra would be Rohini because when the moon appears, that's where it is. So in addition to that, you see these circles over here. These circles are projections of Earth's latitudes and longitudes on the sky. So they become celestial coordinates. So this is the celestial North Pole, 90 degrees, 80, 70, 60, 50, 40, 30, 20, 10, and 0. So 0 is the celestial equator. On the day of the equinox, the sun would be exactly on the celestial equator. Okay, so the Uttarayana is 6 months of a northward course of the sun. So it goes up to 23.3 degrees north. Then the sun retraces, crosses the equinox, and goes minus 23.3 degrees to the south. Indians knew all these things. So these were the cardinal positions. So they could look at the sky and figure out the extremal points, where it should come, and what is the nakshatra against which a certain solstice or an equinox would appear. And they recorded these things. They recorded these things in many, many of our texts. Based on that, we can have an understanding of how ancient these things are. One big example is the Vedanga Jyotisha. Vedanga Jyotisha, they've got two components, the Rig Vedanga Jyotisha and the Yajur Vedanga Jyotisha, and they've got these verses 5 and 6 and 6 and 7. These verses say there was a winter solstice in the Dhanishta Nakshatra. So the colonial Indologists tried to make sense out of this winter solstice, the Dhanishta Nakshatra, and they cranked back because of precession. That's no longer a true statement. When winter solstice happens, we are not at Dhanishta Nakshatra. It happened in the past. So they cranked back in time and tried to figure out when did that happen. And various scholars gave various times, but the closest was Colebrook and Dikshit, who came to 1400 BCE. And it turns out that I simulated this in the calendar and planetarium software. Winter solstice happens here when the sun reaches 24 degrees approximately over here to the south, and here is Dhanishta. So this clearly shows 1440 BCE would be the date for Vedanga Jyotisha. Why is that important? It's important because you can use this to debunk some of the things that Max Muller did. Max Muller had used a linguistic model and tried to say that the Chandas period is one, the Mantra period is one, the Sutra period is one. He crammed all these things from 1200 BCE to around 200 BCE. And he said that the Jyotishas are the last Sutra period composed between 600, not in 600, maybe 300 BCE to 200 BCE. But then the Vedanga Jyotisha seems to have been written in 1440 BC. So this was a huge hit to him towards the end of his career when people criticized him saying, what about this? You're talking about a particular date for the Vedanga Jyotisha, but the astronomy inside says 1440 BCE. This led to certain things in predictable ways. I'll talk about that a little later. Shatapatha Brahmana Yajnavalkya has got a statement that Kritika never swerves from the east. I'm not going to go into details of all of these things, why it was so, but you have a heliacal rising of the Kritika nakshatra, and this would have happened on an equinox point, and this equinox point is a circle, and what you see is that this particular date works out to 2982 BCE. Again, it's an affirmation of the antiquity of a Brahmana period. Again, it goes back and hits against Max Muller's dating, who said that Brahmana period is 800 BC and so on. You have a pretty ancient data encoded inside Shatapatha Brahmana. We have an ancient epoch encoded in tables. I'm not going to read all of these things, but many of the Puranas, temple epigraphy, and books like Surya Siddhanta and others seem to be referring to an epoch that is pretty ancient. So this Lee Gentle, who came to India, he's a Frenchman who came to Pondicherry. He got some tables from the Brahmins and published it as Tables of Trivellur. He sent it off to his friend Cassini in Italy to analyze that, and Cassini came back and said that it refers to an epoch that is midnight of February 18th, 3102 BCE. So all of these things are referring to that particular epoch, and that turns out to be a rare conjunction of planets, sun, moon in the Revati nakshatra. And some people refer to this as the start of the Kali Yuga, and also an attempt to do a dating for the Mahabharata. I know there are multiple opinions on this, but this is one of the dates for that. So simulating this in the planetarium software, you say February 18, 3102, here is Revati nakshatra. This is the ecliptic on which all the heavenly bodies go. And you find Jupiter, you find Venus, Moon, you find the Sun, you find Saturn, you find Mercury and Mars. All of them are clustered in the Revati nakshatra. A very, very powerful affirmation that there's a Vedantic concept in an epoch of time in which the so-called Aryans shouldn't even be in India, because they are supposed to come only in 1500 BCE. Very, very powerful statement. I'd like to talk to you about Aditi, who's the mother of the gods. Aditi with Kashyapa gave rise to Adityas, Rudras, Vasus, and they're supposed to be the Devas and the Daityas. Bhagavad Gita talks about the 6-month course of Uttarayana, which is the path of the Devas, and then the path of the Daityas, which is Dakshinayana. And we get the impression that the mother should be equidistant from her sons, whether it is Devas or Daityas, she's got to be equidistant. So you get the feeling that there's something to do with an equinox and Aditi over here. If you're thinking that, you're right, because that's what happens. Now for Nakshatra Punarvashu, the deity is Aditi. I'm not going to go into great details of why that is, but Balagangadhar Tilak as well as Abhyankar called this out and said that the era of Aditi is 6000 BCE. It refers to the vernal equinox at Punarvashu Nakshatra. And you find that the vernal equinox position is over here, and the nakshatra at that time is Punarvashu. If you simulate this in the planetarium software, it comes to 6000 BCE. So this is the era that Abhyankar and Balagangadhar Tilak referred to as the era of Aditi. There's one more interesting data point with Ashwinis. Ashwinis are there all over the place. We know about the story of Sun, that he married Sanjana, and they had twins, the Ashwinis, and Sanjana couldn't take the heat, so she decided to run away from the sun, as far away as she could get from the sun to be cool. If sun was in the winter solstice, Sanjana is in the summer solstice point. If sun was there, she's as far away from the sun as possible. She did that because she wanted to go to the cooler region. She left the shadow Chaya and left. And you find that there are a lot of mentions of Ashwinis in the Rig Veda, a lot of verses over here. Our ancients did not just say these stories because they loved to say stories. They were encoding astronomical information in some of these stories. So this particular episode, along with this information of Ashwinis, is interpreted by Tilak and Abhyankar as a heliacal rising of Ashwini Nakshatra. Because all over the Rig Veda you find verses like Ashwinis appear at dawn for their share of sacrifice. Okay, Ashwinis appear at dawn for their share of sacrifice. Based upon that information, you see the heliacal rising of Ashwini, winter solstice, because in the northern hemisphere that's when it's cooler, because that's when Sanjana has fled from the sun and so on. And this turns out to be 7200 BCE, very, very early time frame in the Rig Vedic period. And there are a whole lot of ancient observations. I'm not going to read these things. P.V. Vartak has got about the seasons, the Rig Veda, and various other texts, Puranas, and so on. A whole lot of dates over there. So what I've done so far is trying to emphasize to you that many of our ancient texts are encoding early information as stories. So these stories are there in the Rig Vedas, in the Brahmanas, and other places. If you do not know the key to unlocking that wisdom, it's a silly mythological story for you, which makes no sense. But if you knew what the significance was, you suddenly see they're encoding dates, they're encoding information, and so on. I refer you to a talk of mine, TED Talk, where I talk about some of these things, how information is encoded in stories. So Siddhantic astronomy is a particular phase when Indian astronomy went from encoding stories as metaphors and so on into using mathematics to understand the course of the heavenly bodies and so on. We know that there were many early Siddhantic works that are lost. The Surya Siddhanta talks about these things, but it also says those works are no longer available. Even the author of the Surya Siddhanta is referring to such an ancient epoch, saying that those works are not available anymore. That's what you see over here. So the texts are lost, but the citations remain. This shows a gradual development of mathematical astronomy in the ancient past. It's very, very important because all of a sudden you have Aryabhatta there with an enormously developed mathematics, leading us to critique that maybe Aryabhatta got his knowledge from the Greeks and so on. This is the critique that comes out against us. But then when you look at the antiquity of some of these works over here, it's clear that there's a gradual development of mathematics. I'm not going to read all these things. There's a deep tradition of mathematical astronomy, whether you look at Vedanga Jyotisha, Surya Siddhanta, Vasishtha Siddhanta, Paitamaha, Romaka Pulisa Siddhanta, Aryabhatta's work, Varahamira's commentaries on the five Siddhantas, Mahabhaskariya, Siddhanta Shiromani, and Nilakanta Somayaji's work, Yukti Bhasha, and Siddhanta Darpana that we talked about. A lot of information that there's a tradition of knowledge in India, a slow growth accumulation of knowledge rather than a borrowing of knowledge from outside. Till such point, when we came to Nilakanta Somayaji, he already had a partial heliocentric model. He had a model in which he thought the Earth is stationary, the Sun is going around the Earth, and all the planets are going around the Sun. So he said that Venus, Mars, Saturn, Jupiter all go around the Sun, and the Sun along with all these things goes around the Earth. And the same model was used by Tycho Brahe in Europe. So you see, there's a transmission of ideas from one place to another, giving rise to a continuity of thought. Well, there was an early attempt to discredit Indian astronomy because, like I said, Max Muller had come with a certain linguistic model and dated some of the Vedas to certain periods of time. And it turned out that somebody came and confronted him and said that, Vedanga Jyotisha is 1440 BCE. Rig Veda seems to have Aditi's episode and Ashwini's episode, Balagangadhar Tilak. He called out those criticisms. Confronted with all these things, Max Muller finally, in this book, he writes a foreword, very fiercely defends his position, and he says he can accept only Colebrooke's date because 1400 BCE is after Aryan invasion of 1500 BCE, and others, he says, Hindu astronomy is unreliable. Same thing with this gentleman over here, John Bentley, says that Hindu astronomy is unreliable. And these kind of views are loosely flaunted to the present times by Indic scholars. I have talked to professors who are living today who you'd normally think are Indic scholars, but even they have espoused views like this, saying that Indic astronomy is unreliable. I think you can make such statements only if you had no idea about Indic astronomy, then you would make these kind of silly statements. I talked earlier about Otto Neugebauer. He is a very powerful man who set the stage for how Western world views Indian astronomy, Indian mathematics, and so on. This is a book that he wrote, Exact Sciences in Antiquity. So his claims were the length of longest to shortest day is 3:2 in both Hindu and Babylonian astronomy. Starts on page number 162. He makes a claim. So he starts seeing parallels in Babylonia as well as in Indian astronomy. He says Varamihira, as well as Lee Gentle, who saw how the Tamil astronomers were using calculations to make duration of eclipse, when the eclipse will start and so on. He encoded this algorithm. They actually went through a process of half an hour of calculation using shells and so on. So he made a note of all their calculations and sent it off, and based upon that, he's saying they use something called linear function to compute the moon's motion. That's what the Tamil astronomers were doing. After half an hour of calculation, they said the eclipse will start at this time, eclipse will get over at this time, this is the duration of the eclipse. All that, he said, is exactly the same as what was done in Babylon. In page number 165, he makes this claim, something called a zigzag linear function. The terminology as well as the zodiac name, he says, matches Babylonia. Varamira, he says, incorrectly copied constants of planets from Babylon. And he concludes that Indians copied astronomy from Greeks and Babylonians. Now, I strongly urge people to read Subhash Kak's work on Babylonian and Indian astronomy, Early Connections, where he makes a powerful rebuttal of all of these ideas. So please do read this particular work. I'm not going to go into details. His student was Pingree. So Pingree was Otto Neujbauer's student, and he mistranslated a Nepali copy of this Yagnaveshwara's Yavana Jataka. And he continued claims of his teacher in Indian astronomy that we incorrectly borrowed from the Greeks and Babylonians, the ratio of 3:2, use of linear functions, use of water clock, concept of Tithi, use of 2 intercalary months, that is every 5 years it synchronizes, concept of 5-year yuga. Once again, refer you to Subhash Kak, who does a concise rebuttal of these things. Also, K.S. Shukla. Shukla has also basically debunked some of these works that he did, as well as Bill Mark. He's also recently come out with works that says Pingree fabricated findings, misread and conjectured to arrive at conclusions. Very, very strong statements from both Bill Mark as well as Shukla that Pingree had made incorrect understandings of Yavana Jataka and the translations of those things. Anyway, these are the received wisdom that we have today. Nobody questions Pingree and nobody questions Otto Neujbauer. So whenever you see works that claim that Indians got knowledge from the Greeks or the Babylonians, you should understand that they are using Neujbauer's works as well as Pingree's works. This lady is the student of Pingree. So it's a 3-generation parampara now. So she's a Kim Lofker. So she critiques Subhash Kak's astronomical code of Rig Veda. She subscribes to the Aryan invasion theory, this book on mathematics in India. In page 6 to 8, she says that she's leaning towards the Aryan invasion theory. If you subscribe to Aryan invasion theory, you have some constraints put on your thinking. You cannot go outside those constraints. Those constraints will require you to assume knowledge came into India from outside. So once she does that, she also appears to be open to the Babylonian transmission issue, whether it came from India or Babylon. She appears to be open to that. She discards the idea that Kerala school influenced Europe. In these pages, she says that there's no influence of Kerala on European mathematics. Again, that's based upon certain assumptions that Vish and other such things. On the whole, she's got a refreshing book, but it's got a strong Eurocentric subtext, and you need to be careful reading that. She reconstructs Parameshwara's expansion of the sine function and shows because of the factor of 4 instead of 6, she says it was a crude approximation rather than understanding Taylor's series. Taylor's series is a mathematical entity where you take a nonlinear function, you can expand it as an infinite series. This is the basis of all of our today's technological works. It's the basis of that. Once you have a linear function, then you can start doing predictions and things like that. And it appears that Indian mathematicians from the Kerala School of Math had up to 3 terms of the Taylor series. Taylor series is the later term that came, but then up to 3 terms. Because a factor 4 was used instead of 6, she says it was not based on understanding but by a crude approximation, and she shows how that approximation was got. In other words, she's working just like Pingree and just like Otto Neujbauer to show that Indians got knowledge from Babylonians and Greeks. So they had to labor very hard to go against the flow because there's overwhelming evidence from this side that says that Indian knowledge went to Babylonians and the Greeks. So that is what it is. Conclusions. Initially, astronomical knowledge is encoded as stories. Later, Siddhantic astronomy saw a strong development of mathematics. We have a long trajectory of knowledge from earliest works of Patani Samanta. Mathematics, partial heliocentric model was the heights of accomplishment. Astronomy learning was greatly impeded by Muslim invasions once Ujjain was destroyed and so on and so forth. Many of the knowledge systems are gone. Eurocentric attacks on Indian math and astronomy from colonial to present times are dictated by deference to the Aryan invasion theory model. So if you debunk the Aryan invasion theory model, all these constraints fall. None of these assumptions are true anymore. The field is open to fresh interpretation and other things.